the second hand is on the street. We're very delighted today to have our distinguished lecturer, Elias Bareinboim. Elias is a professor at Purdue. He's done tons of amazing work in the field of causal inference. It's both its theory and its application. He's done really wonderful work in all aspects of causal inference in relationship to fairness, counterfactual estimation, selection bias, just to name a few papers that I read recently of his. He's received many accolades and awards for his research, among them the IEEE AI 10 to Watch and Best Paper Awards at some of the best conferences. He's really a deep thinker in this field and a passionate scholar, and welcome. Thanks for coming.
Oh, thank you, David. Pleasure to be here. Thank you, David, and the Department of Computer Science for receiving me. Today I will be talking about causal data science, or a general framework for data fusion and causal inference. As a disclaimer, I think beforehand, is it very loud or okay? Is it good? Okay. Beforehand, I would say that no one really knows what data science means. We just kind of have a feeling that it lives in the space in between computer science and statistics. One of my goals here is to say that it will intersect with causal inference, or is very related to causal inference. Perhaps this may be less controversial today than maybe a few years back, but I think this will be one of my goals, and also try to say that we do have a lot of results, or some of the building blocks to hope to have a theory of what could be data science, or to avoid political problems, I try to qualify it, put causal data science, even though I think this is data science, that we have some of the building blocks to be able to claim that we have some type of science, despite the science in the name. Then I would like to start talking about some of the aspirations and challenges that you can have about what would be modern data science around 2019. We have this quote by, probably you know Hal Varian, that's chief economist at Google and professor in Berkeley. They say the ability to take data, to be able to understand it, to extract value from it, to visualize it, and to communicate it. That's going to be hugely important in the future, and he goes on to talk about how in the future people in the high school should have this type of skills. Then we have Gary King, that is a professor in political science, a university professor in Harvard, saying that big data, I would say data science, is not really about the data, which some people may consider funny or / surprising. And then we have Yuda Pro, professor at UCLA, computer science and statistics, saying that data science is only as much of a science as it facilitates the interpretation of data, a two-body problem connecting data with reality. Then those are kind of nice aspirations, or kind of very big picture view. You start from data plus a lot of things saying here. I think the key for us is what it means. Oh, perhaps in the past, people say that the statistics is the science of summarizing data. Now we have a more general, a more aspirational goal that you say the ability to take data and to be able to understand it. Extract value is already the second thing, but to understand it. This is the important. Now here we're saying that the data is not the most important thing, and then Yuda or Pro saying that, oh, there is some type of connection that you like to make to data with outside the world. Those are kind of deep thoughts. And I would like to move and contrast that with the current state of affairs, or how I like to say is a field report, or report from the trenches, what's going on in reality, despite these big thinkers and nice views, these beautiful views. You have this is gotten from the CNN, but this is trying to mirror something that you find in the medical studies that's saying that a study in heavy coffee drinking in people under 55 linked to early death. Then the key word here is linked to. In some way, people want to make the causal statement, because if you say that it's correlation, people could say, who cares? Congratulations for the study, but I would just ignore it. But you are kind of a little bit shy, because you can be held accountable, or someone will hammer you. Then you kind of suggest without being liable, and then you say link to. But apparently there is a kind of negative effect. Then if you kind of read the annals of internal medicine about the relationship of coffee consumption with mortality, there's a somewhat more subtle message about this causal relation. Now perhaps you can go to something more interesting to some people that like to drink socially or responsible. Be careful, guys, or kids. There is some alcohol causes 20,000 cancer deaths in the US annually, which seems to be a pretty devastating piece of news. But then you go on to something a little bit more positive, saying that 1 drink of red wine or alcohol is relaxing to circulation, but 2 drinks are stressful. Then at least you can have a little bit of fun and a glass of wine. And then you go to the good part. Let's say, why do heavy drinkers outlive non-drinkers? And I hope that I will be in this group in the future. There is some sampling issue here that people is kind of dropping out or quitting. There's a sampling problem. But anyhow, I hope I will be there. And then you can go on in the literature on and on talking about the effect of grapefruit, or this one is the association of nut consumption with total and causal and specific mortality, which is some kind of nuts. And this is from the New England Journal of Medicine. This is kind of common theme that every X amount of years or X number of years, let's say 2 or 3 years, you have some type of flip in the conclusion of these studies. What should we do? And I just picked some examples in the public health domain that has an immediate effect in the life of people because this is guiding how you are eating. But this is also true in economics. We are considering about charter schools versus public schools. Or we are considering the effect of a new taxation scheme, a new taxation strategy. What will happen? I cannot do an experiment in the population to see if I will break this population or if I will be able to get more money and kind of create a positive feedback loop. Then those are common questions. And the question for us, or you should be asking, given that we have this flip, is like, what's going on here? The piece of news that I just saw in New England Journal of Medicine. This is the, if you're computer science, maybe you not know, but this is the top journal that you can have in the medical field. The best and the brightest are published in there. They're amazing. And still we keep going again and again, getting this type of apparently contradictory type of results. Then what's going on here? And that should be your question, or my personal hypothesis is that there is some type of tension, methodological tension between the type of data that we are getting and the type of statements that we are trying to make about this data. That is at the core of the discussion of what data science should mean. And the practical question here is like, what should we do with the data, given that we have this tension? How do you use that in a proper way or in a principal way? This is what we are trying to answer. Then the goal of the, let me tell the goal of the talk. In order to avoid following in these traps, the goal will be to develop machine. This is a computer science, using my computer science hat. Develop machinery, and what I mean by that is language, conditions, and algorithms for performing 2 tasks. First task, learning about population-level interventions, or causation as called, by combining multiple heterogeneous data sets. Many works here. This is I just speaking kind of sneak peek. There are many papers. The one that I would like to mention, there's a summary if you just want to have an idea what's going on. It's not exhaustive. Is this proceeding of the National Academy, causal inference and the data fusion problem. But there are many papers that came after that, and there are a lot of work. I can discuss future work, what is still missing from this picture, but this is our first task. The second task will be deciding individual level or unit level treatment by leveraging the data that we have of the population. Intrinsically, in causal inference, we have population data. For sure, you can condition in many covariates or create buckets, but in reality, you never can observe the causal effect for this individual under multiple conditions. Then you have the tension of how to move from population level to the unit level. At the end, you want to do personalized, some type of personalized treatment. We like to be able to claim that it's personalized and not just a bucket that is very fine-grained. Then what the heck this means? Then this is the second kind of goal. Many papers, it's kind of more recent work, I would say. And it's very related to what we have in machine learning. Very related, but not the same, called reinforcement learning. And I'll try to discuss a little bit that towards the end. Then going back here to our problem, abundant amount of data doesn't immediately, then the headlines translate into causal insights. Then everyone is excited here about having a lot of data, myself included, but I like this challenge or this sentence that you have, let's say all data is not created equal. Let me read it. There is a lot of data out there, but this data is almost invariably collected under heterogeneous conditions. What I mean by that, overloaded word heterogeneous. Let me try to give meaning for that, and we'll formalize. Under different experimental conditions, the underlying populations are different. The sampling procedure is not randomized. the treatment assignment is not randomized, and many variables are not measured, or they are not measured consistently across studies. In other words, data collection is messy, not excuse to not try to do it with serious theories. Exactly the reason that we are doing it. If it was messy, we don't need any theory. Data collection is messy and rarely perfectly matches the target of the inference, the quantity that we want. The positive, if you want to be positive, you could take this as negative. I don't take it, but the positive here is like, oops. The positive here is that all these dimensions are now formalized, and there are conditions and algorithms to understand, giving a data collection, what is entailed, what can be inferred from this data collection. Let me try to ground a little bit this heterogeneous data. Suppose that you have a target of inference that you want to get the quantity, the Q, P star of Y given to X. The X here means the treatment or the exposure, if the guy gets higher education or not, or if the guy is getting the drug or not getting the drug, or if he's being exposed to advertisement or not, if you're Google. And Y here is the outcome variable, which means earnings after 5 years of graduation, or if the guy recovered or not, or if the guy's click-through rates after you're showing the advertisement. Then X is the treatment or the exposure, and Y is the outcome. Here you have star to encode that this is the target, and then you have the do. The do here means that this is a deliberate change in the variable X. It's the causal effect of X on Y, which we want to contrast during the talk strongly. You want to contrast strongly with the P star of Y given X. Y given X is just, I usually remove the P. This is my habit. I just say Y given X, Y given to X. Otherwise, you'll keep a P. Not good. The P star of Y given to X, P star of Y given X is the association between X and Y. If you just passively collect data. Then we don't want that, we want the P star of Y given to X. Another notation for that is Y sub X. Now that's good, and then you have these multiple data sets 1 to 3. The dimensions that I mentioned before is like first dimension, the first data set here, this is just the columns of the data set. The first dimension here is that the data set is coming from LA. And this is a different population than the second data set that is coming from New York and so on. Then dimension 1, what's the population? Say the populations are under different populations. Populations are different. The experimental conditions are different, I said in the previous slide. Then this is experimental condition. Is observational or experimental? Here is experimental. And if it's experimental, we need to know what was experimented on, or what we randomize. In this case, in this first data set in LA, we randomize Z1. Perhaps we want the effect of X, that is the cholesterol, on Y is heart failure. But you're just able to randomize Z1 that could be, I don't know, the diet of the person. It's very hard to randomize the cholesterol because we cannot open the patient, throw a die with many levels of cholesterol and set the cholesterol of the person. So there is a causal effect there. Now we are able to randomize the diet, do Z1. And this is the dimension. From New York, you just don't have non-experimental data or just observational type of data. Third dimension, what's the sampling that you have there? Is it a random sample or no, there is some kind of sampling bias? The first data set coming with the bias from the age. Perhaps in the study or in LA, people that how they are recruited usually you call the landlines, but people under 30, maybe under 35 or 40, not even have landlines today. Then you have a mismatch between the proportion of units in the population. In New York, it was about the socioeconomic status of the family. People that has more money, perhaps they are reporting more likely because they are more proud. And people that has less money, they are hiding or not going so much. Then this is the third dimension. And the fourth dimension is like what's measured. Here perhaps you have time series type of data, X1, X2, and so on. Every month someone will come. In the first data set, you measure X1 and Z1, but you are unable to catch Z2 and X2. In the second data set, you are able to get the X2 as well. And you don't have consistent measures across data sets. Now I'd like to tell you, put this in context, and just, this is usually a question that I ask, like what did you do and what was in the field? Let me try to draw a line here, cannot be more explicit than that, to understand what's going on recently in the field. Some common inferences that we have in scientific circles, I would include AI and ML as well, involving a standard assumptions. It's funny to say this one, people find, I think it's important. What is statistics in the descriptive way, or the classic way, is essentially when you are trying to move from the samples of observational distribution, this passive data collection, you are trying to move from by the way, what's changing is the red thing here, or orange. We're trying to move from sample to the distribution. That's what statistics descriptive means. And a lot of the work, and what I mean by statistics are results of these guys, like Bernoulli, Poisson, Kolmogorov, we can go to get Cardano, that is trying to say, under what conditions can you move that? If you think a little bit, you take for granted, it's a crazy move from the sample to the population. Those are results that you have, I like the law of large numbers of the central limit theorem and so on. This is the serious and the principle stuff that you have, how to do this extrapolation. Now we have another branch of the statistics, that is the experimental part, that we are trying still to move from sample from distribution, but starting from Fisher. Some people believe that is before. I like to attribute to Fisher, and we can discuss the history here. This is my personal reading, by the way. But we move from samples from the do-X distribution. Was the guy that had the idea that I want to flip the coin during the treatment assignment, or the decision. And then we randomize that, we are able to get samples from this distribution, and we would like to elevate that to talk about the distribution itself. Still from sample from distribution, but now this is our window to talk causality in the domain of statistics. Now we have a different animal in the room that's called causal inference from observational studies, that now no longer we are talking about from sample to distribution, different beast. Now we are talking inferences across distributions themselves. Then we're already assuming a way that is not realistic. You can relax, so there is a lot of work. But you assume a way that you don't have the sample problem, because this is also a problem. You want to think them separately, and reality will come together later. That is, we are moving across distributions. We have data from a distribution OBS, and you would like to do the inference about the do distribution, for example. Huge amount of work on that. This is my personal reading, causal inference from around 74 until 11. Was mainly concerned about what's called confounding bias. Confounding bias is just the difference between these distributions. And has been solved. I put here quoted before people shoot me. It has been solved by Rubin, Robbins, David, and Pearl. And what I solved, I mean that this arrow here, under what, this is like took 30 or 40 years to understand under what conditions could we do that. Then we understand you have languages, you have conditions, you have algorithms to do this type of inference pretty well. In practice, we can discuss how hard it is. It is hard, but theory proved complete in some formal way. If you have computer science in the room, I can make the statement later, but that's what is called causal inference. Now that's nice, very beautiful. Now the kind of common question that I get is like, is rhetorical. Elias, are you saying that we are done? Because this seems to be pretty good. And also, this is some people that is less positive say, oh, this is old stuff. Where does the causal data science that you are trying to be a big fuss out of it comes into play? Is this just that? Now what I will do is the following. I will just replace the first line here, and I copy what I have in the previous slide, talk about these dimensions, 4 dimensions. We have the different populations, you have under different experimental conditions that can be observational, experimental. You have different sampling conditions, the sample is not randomized, and you have variables that are not measured consistently across settings. And I will just, computer science trick, I will just parameterize that in terms of these dimensions. The observation 11, parameterized. Let me read one of them just. Now I'm claiming that causal inference, essentially they are assuming that we are talking about, even though we have a different regime, observational to the do-X, we are assuming that we have the same population, D1 here. We are assuming that we have the same bias of sampling D3 here, and this is what is causal inference in this schema that we have the dimensions that we have. This is my trick to show these dimensions. Now, the natural question that do these dimensions exhaust all the possible data collection modes that you can have? My claim is no, and I will show you, this is an obvious statement in retrospect, but this is causal inference. I just copied, remove the sample, the clutter. Now, give credit for credit is due. Now we have something called experimental inference, I like to call, that now we are moving from D1, D3, and D4, but we are having data that is coming from do Z, and you would like to make the inference about the do X. This started in some kind of basic way by the Wright families, a father and a son, Philip and Sewall, and around the 20s. The discussion about who gets the credit, I can tell you later. I need 5 minutes, but the point being that this is like hinted there. Now we have another type of inference that I already alluded to, that is sampling selection bias. You pick 1, 2, and 4, and then you have data that is selective pressure on age. People that is younger is reporting less likely, and then you like to make a claim about if you have a represented population. It's a match in the proportion. Then this is a guy called Heckman, James Heckman, a professor in the University of Chicago, in economics. He got the Nobel Prize for showing that not in age, but in terms of something called reservation wage, it's the wage that you'll be willing to work. You just have observed wage, that is the people that is working. This is a measure that is important for economic theory that move the economic agents in some way if you have unemployment. He showed that was possible. He was first proof that I know nicely that it's possible to move from this data collection that it has with this bias to the whole population and design beautiful economic theory. Then, congratulations. Now we have another one that I like. It's called transportability. In the science, it's called external validity. That we are trying to move dimension 1 now. This is dimension 2, dimension 3, dimension 1 that we do all the time. You collect data on bonobos. Not that you like bonobos, they are cute in some way, but we have data on bonobos, but in reality, because we want to learn about ourselves, about Homo sapiens. Now, question is the same. Under what conditions, by the way, this Childish, Cook, and Campbell, there is some kind of basic version of that, or initial version of that, I should say. But the question is like, in general, under what conditions can you move from bonobos to humans? Now, my comment here is this is EB, how we change messages in the lab. EB statement. Special cases of these dimensions have been addressed in the literature, mostly in isolation and under very special parametric conditions. In practice, they appear together in what I'm trying to call, I hope you buy it, this is the idea, causal data science. That we have a collection of data sets in the space of these 4 dimensions. Could be more, by the way. I'm just telling you the 4 that I understand more and we have more theory. We have these 4 dimensions, and we like to do the inference about the target domain. This is what I'm trying to call data science. Today I'll be talking more about this guy that is the transportability, because it's very hard in half an hour to talk about all the variations in one shot, and exactly about under what conditions can you move, what does the arrow mean. Then let me talk about transportability here. Let me first read the research questions. Things are lost when you just start jumping in. The question that we are trying to answer is the following. Is it possible to compute the effect of a treatment variable, that's called X, on outcome variable Y in a target environment pi star, where no experiments can be conducted, using experimental findings from a different environment pi? Then you have 2 environments, pi and pi star, 2 populations, pi and pi star, and we can collect data in pi, and you like to make in pi star, we have experiments in pi, under what conditions can you extrapolate? The answer is like maybe as expected, sometimes yes. The technical work here is like to understand when and how this is possible, under what conditions this is possible. Excuse me. Now let me this is very related to what we are doing in the lab. The basic scientific, and lab here I mean environment, population, domain. Lab is this baby place or small place, metaphorically, that you have these variables x, y, w, and z. And the place that you can go there, shake the system up, do experiments, knock out things, and do whatever you want there, and you can acquire causal knowledge there. One thing that I didn't say here, I forgot. Usually when I write this model here, I'm not being a Bayes net or anything like that. I mean a structural causal model. I didn't do the introduction here. And what I mean by that is like every time that you write an arrow, here's the semantics. Every time that you write an arrow from z to x, it means that there is this underlying mechanism, f of x, that takes as argument or is listening, this is the metaphor, x is listening to z through this mechanism f sub x. There is another mechanism for z. If z has no parents here, then z is just listening to some kind of exogenous variation. This is what's called structural causal model. There are axioms and it's well formalized. But anyhow, we're going back here. Then you have the lab that you could acquire experiments. Now, usually you don't do experiments just for the sake of doing the experiment sometimes, but not always or not usually. Usually you like to make a statement about the world. Now the assumption that the scientists face here, the hypothesis one, is that lab is just a smaller version of the world, but they are qualitatively the same, which means that the statement here is that f of z is equal to f of z star, f of x is equal to f of x star, and so on. All mechanisms are shared lab and outside the lab. If that's the case, a theory that does some type of transportability of extrapolation, say everything is assumed to be the same, trivial. Just copy the results from the lab to outside the lab. So a hypothesis usually will not hold because it's too pink, too good to be true. On the other side, the nightmare scenario here, now I'm adding these yellow arrows. That means that potentially the mechanisms can be different. Then we're encoding that the f of z is possibly different than the f of z star. F of x is possibly different than f, and so on. If that's the case, some people don't like it, but from the theoretical perspective, very easy. Nothing can be learned. Everything is assumed to be different. No learning can happen. This is like we are collecting the lab is Escherichia coli or some kind of very low-level organism, and we are trying to learn about human cognition. There's no hope that you can learn something from E. coli to the humans. Then that's the answer from the theory. The literature oscillates between these 2 points almost invariably, and it turns out the observation that there is a whole spectrum here. There is the whole spectrum of possibilities here. We learn things, right? Science progresses, you learn things that is invariant between places that allows us learning to take place. The question is like, that is exactly within this spectrum here. Now let me show an example what could be in the spectrum. Let me add a little bit of concreteness. Question is, what can experiments in LA? LA is the pi. The source population can tell us about New York, that is the target pi star population. Here we have the same type of diagram that I just showed. And the assumption of the diagram here, in the same as usual, the graphical models, the information is not in the arrows, people find funny, but are in the missing arrows. How you have a missing yellow arrow pointing to y. What it means that we are claiming, this is a super strong claim, that in this level of granularity of the system with x and z, the y, f of y is shared. F of y is equal to f of y star. And this is the statement. Then we are agnostic about what's going on with x and z. No claim. Then we leave the arrow, yellow arrow there. Now, and by the way, you are trying to get the effect of x and y, and you have age as a covariate. And this is a qualitative understanding about the system. It's part of the input of the problem. Now, another piece that you have as input is an experimental study in Los Angeles. In the source, you are able to randomize or to control the value of x. Then you get this distribution, P of y given do x comma z, the effect of x and y for each age group, called z-specific effect. Great. And you also have another piece or another data set that is the P star of x, y, z. You cannot do experiment in New York, but you can do random sampling in New York and collect non-experimental or passive data, observational data. Now this is input. That's just a prototypical problem here, just trying to solve the X-ray here or what's going on. The output or what we're trying to get from this analysis is the query or the quantity is P star of y given to x. Can you predict the effect of the intervention of x on y in New York? Then summary, we have qualitative understanding about the source, the relationship between the source and the target, and you have 2 pieces of data or evidence or quantitative evidence, the experimental data set in the source in LA and observational data set in the target in New York. And the question is like, can you predict the effect of the intervention in the target? It turns out that for this particular example, there is a solution. There is a, yes?
Just a clarification, the horizontal arrows, are they different from the vertical arrows?
What's that?
The horizontal arrow on top for Z?
This arrow here?
Yeah.
Yeah, all yellow.
Vertical arrows?
No, they're just yellow. No, it's just,
Okay.
yeah, no difference.
It's not
Yeah.
I have a different clarification question. Could you please explain for me simply what is the difference on doing an experiment in LA and doing an observation in New York? Isn't an experiment also characterized by observation? Isn't every observation a formal experiment?
I'll answer in a short way because we spent maybe one week in lecture discussing the tension between the experiment and the observation. Then I will give you the 15-second answer, and I can take it offline. What we mean by do is like we are deliberately go into this variable x, get with our hands, and start moving x and seeing how y is moving. This is called experiment. And our metaphor, the muscle that you use to move, this is the coin, for example, the FDA is using to do this experiment. It costs maybe $10 million coin to get data of this type. Now, here, we are not deciding how people is getting their treatment. They are naturally inclined based on the age group in picking the data, the drug with different probabilities. Then this is called the natural regime or the observational regime. People, they are free, with their free will, quote unquote, we can discuss if this exists, but with their free will, they are making their decisions.
So just a quick follow-up.
Mm-hmm.
To keep following the concrete example, it's like if the drug is actually available in the market and used in New York, but the way it is administered in LA, you control it.
Right. Correct. It turns out that for this particular problem, there is a way of combining these data sets without having to do this deliberate or this experiment, spending the $5 million, $10 million to get the effect. In New York, we can combine these two data sets in order to get this distribution. And the combination is quite simple in this case. Essentially, from LA, you get the z-specific effect of x and y, the effect of x and y for each age group. You average over this group. And you kind of reweight the new age distribution P star of z. And the idea, quite simple, is like, yeah, we're trying to take into account the difference in the age. They have different proportions in the population. This is what I call transport formula. Some people like to call it recalibration. I dislike, but it's true. That is a name. I dislike because overloaded. It has so many different meanings, different semantics. But anyhow, we are asking about the existence of a function from the distributions that you have, the P, the P-do, P star, to the target distribution. And this is the transport formula. It turns out that this formula is known for more than, not in this syntactic form, but in spirit. Someone told me maybe a few years back, for more than 200 years. And then we went to the papers to try to understand how people that in England, there's some kind of demography, study about demography and mortality. But this is the initial point, and then the kind of valid question here is like, is this a universal law of the data sciences? Any two data sets that you collect that you want to do this operation of generalizing or extrapolating from one place to the other, we just plug in this formula. That's the question. And I would like to, but can I get it offline? Yeah, I will, the offline or, sorry, at the end. I will, unless we are dying inside, I will get it. I don't want to, it's okay? It's okay. And I'm sorry for that. I'm just copying here the same graph that I had before, but now I'm adding this dashed bidirected arrow. This is to make a little bit more realistic in the causal sense, because we are very, very concerned, because the number one concern in the field is about these unobserved confounders. The latent variables, here we have a latent variable uxz that is sitting here between this dashed bidirected arrow that is generating exogenous variations for the x and z. Then our concern that we are looking x and z move in some way. We don't know if this is z making x to move in this way, or if it's this guy, uxz, that is making them to move. The same here, you have a uxy here that is generating this exogenous variation. It's just a piece of notation I'm introducing. But if, this is just the data sets that I copied from the previous slides. It turns out that regardless of these latent variables or unobserved confounders, I call UCs, we still have the same way of combining the data. Now it comes a nice question here, in my opinion, that is like, is it universal, really? Now this is an example. Suppose that you have the same data set just for a relabeling. You don't measure age, someone screwed up, age is not available. Always happens in studies. Now the Z now here is a proxy for age, language skill. Suppose I do discretize in the same number of buckets just to make sense, have the same data sets. Now the question is like, is this formula right? Is this the right way of combining these data sets? And for the guys that understand this separation here, if you don't, just give me 30 seconds, you can see here that whether you call this node the yellow node, the square node, S, just to be able to call it something instead of yellow. You can see here that there is a collider on Z. Then when you condition on Z, we are exactly injecting bias or the source of heterogeneity directly because we have S, Z, age, Y open here. Age is not measured. Then it is a terrible idea because this guy is conditioned on Z. And we don't want to do that. And you can see that S and Y are marginally independent. There is no effect whatsoever. S, there is no direct path from S to X and Y. then the correct thing to do is just P star y do x is equal to y do x. And this formula is wrong, is biased. And this is the correct way of combining the data. Let's ignore this data set, don't do this adjustment, let's use this one. Now you can go more sophisticated a little bit, or more setting, same data set, that's important, same data set. Now let's get a variable that is post-treatment, post-decision. Usually you pick the pre-treatment, Z here is before the decision. Post-treatment, there is a lot of discussions in the literature about these guys, Z. Now the question is like, how do you combine the data? You have the two same data set discretized in the same way or bucketized in the same way. Should we use A, should we use B, or is there something else? It turns out that it's neither A nor B. There's a different way of combining the data. You get still the Z-specific effect of X and Y, and you will weight by the Z given X, star Z given X. The lesson here, sorry. Oh yeah, sorry, how can I go back here? Biomarker, sorry, I forgot even to say the name. This could be the drug biomarker, could be the cholesterol level. Then the drug will affect the cholesterol level, and the Y is the survival of the patient. And the difference between these two populations, maybe bonobos and human beings, the behavior of how cholesterol changes with X is different. The F of Z is different. The F of Y is the same in this case. Now the lesson here that we learn is that causal assumptions are required, since which means these models here, since the data doesn't impose enough constraints over the causal structure. In other words, this data here doesn't tell me which one is true. All of them are compatible with the data. And the results of how you combine the data is sensitive to the structure. Then it's kind of proof by picture. And not it's like we need something like that. Maybe in this form or equivalent form, but there is no escape. Now let me just show the problem. Then this leads to the problem that we call the decision problem. Is the target effect transportable? We have a triplet. You have the query that you are trying to answer, star given y do x. You have a causal model called graph that is this way, this form with this yellow. And you have many data sets. Now, what we're trying to answer, this is TR is transportability. We're trying to answer that based on the current knowledge about the problem that is encoded in number 2 and the available data sets, can the research question 1 be computed, be transported? And it's a decision. Sometimes it's possible, sometimes it's not possible. This is an example that we just saw that is possible. We just discussed this one that is the biomarker, the cholesterol. Then we are saying that there is a mapping from the data, that is observational data in the source, in the target, and experimental in the source, to the causation in the target. That's the problem that we're trying to handle in generality. For any model that you replace this guy, and on any data set that we have, we would like to run this type of analysis. Now, let me try the type of result that we have. Theorem. I'll read it and try to explain. Causal quantity Q is transportable from pi to pi star through this graph G, the causal model G, if and only if the strong result, there exists a do calculus, and I'm not explaining what that, because some type of technical result. If there exists a do calculus reduction of the query Q in pi star to an estimate as a function that is a function of the observed distributions. Show the flavor of how this looks like. This could be the G. You have this P star of Y do X. And then you like to do a derivation. You do step by step the derivation, and you show some type of you show some type of reduction that this is the observed data. Then you succeeded. This is a yes answer. That's what we have. Let me show diagram what this means, or the meaning of transportability. This is the space of all possible models. This is the models in this huge space. This is the model that are compatible with the causal model that you show, the G. You also have the models that are compatible with PV, P star V, and PV do X. Those are the distribution that you observed. Then there are not all models G that are compatible with what you observed. There is this intersection here. Now, when you say that it's transportable, it means for all of these models, that you don't observe the causal model because this is the true nature, they collapse to the same thing. They always agree with the distribution P star of Y given to X. And this is the meaning when you do the inference, just write in a roundabout, I would say, mathematical way. Formally, for any two causal models that are encoded in this unobserved nature N1 and N2, such that they agree with the same graph, the G of this nature or G of the other G, if they agree with the same, agree mean the distribution generated by the first model is the same as the second model for each of the distribution, then they will agree in the thing that you are not observed, that it is the P star of y given to x in both models. This is the meaning of transportability. You don't need, it's almost like I don't care.
Is there always a unique for which that would hold? Can you have multiple G's that could be transformed?
This is for the G that was claimed to be the true G. Then it is G sensitive. I will show you one example in the next slide.
I'm just worried that I might give you a different G. There are two different G's that satisfy this.
Yeah, let me show. Us.
How do I know which G is right?
Yeah, the G is right. Usually, when you write a model like that, I'm not discussing here today, but they imply some constraints over the data. It's not uniquely, but they impose some constraints. Then it's.
Do you trust the person who gives you the G?
No, but you have the important thing is you do have testable implications of this guy over the data. Then you can check if this is at least at some level compatible with the data. The point is like there is some ambiguity, possibly ambiguity here, but I'll try to answer that soon. Now let me show a negative example. This is, oh, I forgot here. So here you observe W. Now suppose that you don't observe W. Then this is the resultant graph when you marginalize W out from the model. This is the same model, could have the same distribution when you sum W out. Now it turns out that this is an example that the answer is no by the theorem. It is not possible to answer transportability. Let me show you what it means. The proof is there exist two models, or two natures, N1 and N2, and I'll show them. I will not read them, but I will show them. This is the kind of the mechanism if you're the god of the system, of the designer of the system. Those are two compatible natures, that these natures have the same graph. They generate the same distributions that you're observing, but they generate the same answers for your query. The P star of y given to x in model 1 is different than the star y to x in model 2. Then this is when you stop and say, oh, this model is not good. Maybe true, but the coercion is not enough to avoid us having to run this experiment. And this is the kind of negative result. Just showing the picture here, this is just copying the other side. But now what we are saying that in the space of the possible models that generate the answer, some of them will give some answer, others will give another answer. Then you don't have a way of moving on in the analysis. We are stuck in some way. And this is the meaning of non-transportability. Then whenever someone says that everything is transportable, I'm very suspicious, because I know that there are negative results. And a lot of work now, my work in particular, is about the negative no answers. I'll talk more about that soon. And the idea here is that then result, we like to pick a graph that is crazy. We don't want to go through the causal logic, but we like to have an algorithm that you can input this kind of model that is more realistic, and the algorithm will say yes or no. This is still a picture, a cartoon picture of a causal model that is possible to have a conversation. In reality, this is the kind of model that you have. It's a model that you work with people in the hospital about ARDS. It's some kind of respiratory disease on the lung. You have some kind of medical ventilation, this is tidal volume, and you are like to have some kind of the settings of some machine, and this is survival. This is more real. You would like, in some way, the goal is to have automated transportability analysis in larger scale. That's the goal. Now, observation here, let me check my time. Yeah, the observation here is that we spend a lot of money running these experiments. The question is like, are they the solution to everything? This is a conclusion of this result, this work. This is suppose that this is the model before you run in the controlled experiment. What the controlled experiment gives us, you randomize X. We are able to unconfound X with all other variables. But still, you don't make any statement or you don't have any control what's going on with the other variables like Z. Now, Z may be the source of disparity. The age may be different, or the severity of the disease may be different across populations, the more realistic one. Now the issue is like, this is an example that is non-transportable if you learn the same kind of analysis, which means that for the disseparation folks, there is a direct path from S to Y here if you don't use Z. But if you try to control for Z as the first adjustment, first formula, you kind of create some dependence to the latent. The S and the U will be correlated there because there is a collider there. Then there is no way that you can remove, this is a no answer. There is no way to remove the heterogeneity. Then the conclusion here, the lesson is like, even if you have a perfect RCT, you spend our $5 million in the UCLA or Columbia Hospital, one still needs to go through this transportability type of exercise. There's no escape in some way. To do some theory is unavoidable. Now, and as I show, it's an if and only if condition, which means that it's complete. Every time that you get an answer, we know that this is not our fault to get a no answer, but there is no way. We can always cook a counterexample similar to the one that I showed. There is some type of factory of counterexamples, depending on the graphical structure, depending on your knowledge. Now let me talk a little bit quickly about what I have been doing. My lab is the Causal AI lab. I believe Causal is important to AI. As you can see, then let me make a quick summary here and tell a little bit about other things that I am working on. I think the first observation, the insight is like, there is a structural causal model underlying this reality, which is a philosophical statement that reality can be decomposed in terms of these mechanisms. They call modularity or autonomy, depending on the literature, the philosophical literature, the econometrics literature, and so on. And then from this structural causal model, you take different set of problems. One of them is just a fancy word at the moment that will give meaning. We try to give explanation. We try to understand something, the composed reality in terms of these more basic and interpretable components. Different tasks in the causal inference literature, one that we discussed, but effect identification is one that I discussed, a general version of that. The composition, bias analysis and fairness is within this, explaining how the variations are working. How can we explain variations? Robustness and generalizability. Transportability is an exercise of generalizability. And there are books or libraries written about that. In the sciences, in AI, is still cartoon to talk explainability. But the take is like, we assume that there is this unobserved set of mechanisms, and you try to do our inference as if you have the mechanism in a principal way without having it. This is why you get no answer many times. Sometimes, yeah. Let me not go a tangent here. The other side of the coin for the structural model is if you want to be pragmatic. So you're not trying to play the science. You're just trying to decide and to improve something, reality. Then you have the decision making, all the decision theories that you have. It's very tightly related to reinforcement learning, randomized clinical trials, and personalized decision making. For sure, this can be, again, many books on that. This can be studied separately. There is some interaction. As much as you understand causally about the system, even if a little bit about this kind of DNA of the system, a little bit, this is already improved. You have paper after paper showing how can you improve decision-making from this causal understanding. And the other way is true as well. If you have an RL type of agent that is interacting and doing causal interventions in the system, we are doing that blindly today in the standard RL, you can learn a little bit about the causality of the system because those are experiments at the end. And that's nice. This is the theory side, the upper part. I'm very interested in the application side. This is one of the reasons that I am here giving the talk. Applications in the health sciences, obvious. We discussed earlier about some applications of computer science. I'm interested in education. This is I'm a professor. And also software development. There's two types of applications that, for the causality perspective, can be the same, but they have very different types of people and they're different in some other ways. AI, we're trying to have the principles and tools for designing intelligent, robust, and adaptable system. And in the data science, that is the one that I talk more today, we are trying to have principles of doing inference from logical data collections. And you like to hope, or at least have some illusion, that you can put this label science or scientific and believing that this is true. This is a high-level picture of the lab. Let me talk about other results in causal AI that I haven't talked today that I think are interesting to the crowd. There's recent work. Excuse me. Recent work in where to do the intervention, called where to intervene or where to do. There's a paper in New Rips and III recent just this year that's saying the following: given a causal model, how to design an intervention that brings about the desired change. Seems to be obvious, but many of the works in the field and everything that I talk until slide 27 is about, I know that the lever that I have in reality is the variable X. And all my efforts is trying to understand the change that X will bring about in the world. Now in this paper, series of papers, and more to come, we are trying to understand how I have this complicated, and you tell me that you have these 7 levers or these 4 levers in reality, X, W, Z, and some other variable, and I want to understand which one should you touch, should you manipulate, such that you want to bring about the change. Turns out to be subtle, and I'm very excited about this work. There's another one that I'm very proud or happy that this got a NSF career on, exactly called approximate causal inference. The idea is the following. All the results that we are showing here is about getting a yes or no answer to the decision problem. Is it transportable? Is it recoverable? So from selection bias or for the data fusion or the data science problem. Now, the yes or no is too brittle in some way. It reminded me of my grad class when I was in grad school taking approximate algorithms. And the theory of folks that have originally, maybe 30 years, have something about the P versus NP. And then people say, okay, maybe it's so hard, let me start doing a principal way of doing approximations. We need the same kind of thing. This is what I'm calling approximate causal inference. I would like to be principled about the no answers that we are getting from the theory. Then this is kind of the first works that I know in the field trying to do that. And this is approximation or in terms of the output of the analysis, the yes or no. Another approximation that I'm interested, that is a very common question, is like, you just ask, like, how do you get this causal model? Then this is approximation or relaxation in the input of the analysis. Now this works here, this in particular, the 18 UAI, is about suppose that you don't have a causal model, but you have an equivalence class of causal models, that are all models that are compatible with the observed data. For sure, naively, we can run the engine that I just showed, but the point that things go super exponentially. Then it's impossible to do it. Now we're starting to have all results that you have for 20 or 30 years on top of this coarse equivalence class that is all learned from data, which is kind of very aligned with the feeling that I want to be more data-driven. Then this is approximate causal inference. Recent work is work that I would like to talk. I need 1 hour. This was my realization to talk about very recent work on the fairness analysis. I call causal fairness analysis. That is how to determine and then to decide if there is unfairness, but determine, quantify, and correct for determine whether a certain decision-making process is unfair when the causal mechanisms are unknown. And if you said that it's unfair, now let's quantify and try to correct. Those are those are type of initial papers on this vein. My take is like there is no way of doing fairness analysis without causation. If you want to ask me during the questions, that I have one slide for that, but I cannot talk now. The other one is like, again, how do you come up with the model? There's a lot of work of how to learn models from observational data, not much work about how to learn models from experimental data. Then how to construct causal model from combinations of heterogeneous of observations and experimental data. Let me skip this one, because I need to say about counterfactual decision-making. That is the one that we talked with Daniel earlier. Now let me conclude. Causal data science, principal way of combining what we are aiming for, principal way of combining substantive knowledge about the phenomena under investigation with the data to generate causal explanations and better decision-making. Now, the insight here or the observation is like, not all data is created equal. Most modern data collections are messy and plagued with systematic biases that need to be understood first, acknowledged, formally understood, and then you can hope if you can control or not or approximate maybe, so that the causal claims can be made. Causal data science, what we have so far of this beautiful picture, in my opinion, my unbiased opinion, I would say a joke, but causal data science solves long-standing challenges in the empirical science, including confounding bias, selection bias, generalizability of experimental studies, and data fusion. The dream or the goal is like, can you have automated scientists? A version that you have automated epidemiologists or automated economics. And the reason here to have hope or to have this dream maybe is like reasoning with cause and effect relationship is part of the core of the scientific method I quoted here. You can ask me during lunch with the philosophy. But the scientific method has been understood in very generality. Then you do have the math and the models to understand what scientific inferences mean. And then the strategy here is, then there's no reason, the note here is like, there is no reason this not to be possible. At least I cannot see that we have some special stuff that will different than the system. Strategy here is combine CI, causal inference theory, with AI machine learning techniques to automate the process and close the loop in scientific discovery. I just want to read one code that I like. It's very related to what we're doing because there's two worlds. development of Western science is based on two great achievements. The invention of the formal logical systems in Euclidean geometry by the Greek philosophers, and the discovery of the possibility to find out causal relationships by systematic experiments, my bold here, my color, during the Renaissance. I think we are trying to be systematic. The world we have been moving in these two kind of extremes. Can you be systematic and combine them? This is the logic of doing experiments. Anyhow, that's it. Thank you.
Yeah, just one quick reaction to the transportability example. You're basically summing up around variable Z. What if Z is complex, can take on many values? What if it's a bundle of random variables?
You mean when you want to do the estimation of this type of estimate, what?
The Py given X and Z is worrisome because you might be summing over an exponential number of values.
That's a real problem. What meaning needs to be done. What I'm trying to highlight, done meaning there are ways of handling that. In some way, you have been studying maybe for 20 or 30 years exactly how to do estimation in high-dimensional Z. But this is not to say that this is easy. That's a hard problem. The only highlight here, I'd say, there is this whole dimension of other problems that even precede we reaching this stage of doing the estimation of. This is the last mile before the victory, I would say. Then this is the take or the bias here in the talk that I'm trying to make sense. Yeah.
Maybe it's handled by special kind of bias, but perhaps should give some thought about adversarial causal inference, because you have so much dependency and belief in the data. So it's not just error, but willful data that's been created by experiment that's false. For example, the university example. Part of it is data that was generated that affected loss for subsequent reasons.
Yeah, that's the meaning. Many ways, this is a longer conversation, but what I can say is like there is not much serious or even work, non-serious as well, in work in the adversarial causal. First time that I even hear this word, but it's a valid one, it's a valid concern. And one of the reasons of some of these results that people, for example, I'm going to the FDA next week. The biggest concern that they have, because there is a lot of opportunity in using, you have sitting here in the Columbia Hospital 1 billion data points. The attitude of the FDA is saying, man, this is crap because there is confounding bias. Let me run an experiment, spend $10 million, run the experiment, and I'll get 300 subjects, and I'll be able to learn the causal effect. And this is kind of nuts. David agreed for sure. So but the main concern, and I'm going there to try to corroborate that. It's obvious that's crazy. But their main concern, that is a valid one, is like this is a huge industry. I think it's more than $100 billion per year that they experiment with that. Just with the experiments. Now, they are concerned about the pharma companies. They could do anything that this is why I'm concerned about being recorded. But it's the truth, and it's fine. The pharma companies this is what I heard from these guys in the FDA. They can do anything to get the drug approved. Then, if you get data from the hospital that is observational and the protocol is much less strict, how can you guarantee that this data is not? And I never thought in this way before. This was recent in the last months that I'm talking with them. Then it is a concern. Yeah, that's I don't think that we have theory. What we do have of results is like if you do run the experiment, and asymptotically, eventually we'll be able to wash out or wash away the effect of the observational data set. But if the prior is too strong, this can take so many samples that then it is a problem. It's a good question. Right, but practically speaking, maybe you can have kind of more constrained settings even when you do observation to guarantee that they have less influence, or they cannot, but that's the discussion, the current discussion that we are having. Yes, yeah.
I'm in humanities, by the way, so, and for us, the question whether two contexts are comparable, we're kind of on the exact opposite end of the spectrum. Historical contexts are rarely comparable, whereas in physics, we can pretty much assume that electrons and matter and
have you heard the second quote?
Right, exactly.
This is exactly the point.
I think the underlying sort of, and you're trying to get us to that sort of, can we have some heuristics about formal comparison between contexts. But,
No, no heuristics. We want to have a theory of how to think about that. But yeah, not heuristic.
But this is, I think, my problem and where I start bristling is that, well, we are applying data science to human-based systems, to New York and LA, to New York of 10 years ago to LA today. Those will never behave like electrons, or there's very stability there is the stability of biological systems.
Uh-huh.
We still have maybe our brains are more or less the same, maybe we react to drugs, but to convince me of that, you really need to develop a qualitative sort of story about which contexts here are, or which systems have changed, or which systems are resistant to temporal change. Human body has remained the same for the past decades, but maybe not for the past millennia. And which systems change rapidly? I don't know, the transportation dynamics of New York has changed rapidly in the past 10 years. Having two data sets from 10 years apart, you're going to have a very difficult time sort of removing, or your causal model will be quite different. So this is where I feel like you're trying to get out of that epistemological bind of understanding the underlying causal systems and having sort of qualitative, historically grounded positions.
Let me try to answer. Just to be fair, but it'll be shorter, maybe. But the point is, like, you read the last quote, right? That Feynman saying that imagine how harder physics would be had the electrons had feelings. That's his statement. I put just after Einstein. But the idea is, like, we are trying to do a theory without having this. These guys are trying to learn the Fs. This is the job of the physicists. It will take 100 years, 200 years, but we will learn the F. It's getting harder and harder, but still, because we already maybe got a lot of fundamental pieces. But this is what their job. Now what we're trying to do is have a formal theory, because all these distributions are entailed by this mechanism. This is what I meant by there is an underlying structural causal model. But you don't have them. Now can you have a theory that will be here rigorous, or you can put the label scientific, as they are, without trying to catch the Fs. And this is useful, I think, except in physics and maybe chemistry or biochemistry. For all other fields, the social sciences or the biomedical sciences, these Fs are so complicated that it's very, and there is the human being in the loop, that as Feynman noted, that is very hard to account for that. Then we are already coarsening, we already operate at another level of abstraction. Now, this is the literature before. The question is, like, if you want to do the inference, to use the data from one place to the other, what we can show that there is no option. This is why I have a if and only if. You need to engage in an exercise like that. And I haven't claimed that it's easy. It's so hard to decide what is the F. Is exactly, this is the only thing, by the way, you can try to learn from data. We have all this lack of identifiability. But the point is, like, this is what we are asking from the scientist. If you don't need that, we automated the loop, the scientific loop. Then you can fire everyone in the other departments. And computer science will be the king. But it is not, we are not there.
We have one more question.
I don't know, yeah, please.
I misunderstood. Actually, there is the opposite problem, because, for instance, transportability, the way it came across, is like a qualitative property. Either a causal effect is transportable or is not transportable. But in a very complex diagram like the one you show, let's say you have two of those and you want to transport one causal effect, and if you don't have a measure, how do you know that you're not just saying, look at this causal effect, and this is all you need to do?
No, look, the exercise is model dependent. Then whenever you tell me that you have two models, we already have something here that is not matching. Now there is another task that is work starting there in the literature, in a general way, how I like, there is 30 years of literature, called sensitivity analysis. Then you could try to do that in a causal way, but still you don't have results that I can say we are...
So basically it's future work.
Correct. Okay. Yeah, and in the science, there is no sensitivity to the model. The model is one of the pieces of the triplet. Then the whole analysis is contingent on having this model. No magic. This is the thing. No magic here. No claim of magic. Yeah, unfortunately. It will be a better place, but it's not true. Doesn't exist.
Thank you, Elias. Very thoughtful.